Okay, happy Friday. Let's do this. Your affinity homework number 3 is due tonight, and then quiz is Monday. So we're going to do differentiability today, and then I'm going to do a couple more examples on like interpreting the derivative. So differentiability. So differentiability kind of comes hand in hand with continuity. Okay. So you remember when we talked about continuity, we talked about the graph, we talked about the 3 different kinds of points where it could be discontinuous, all those things, right? So differentiability, the derivative exists for each point in the domain. The graph must be a smooth line or curve for the derivative to exist. In other words, the graph looks like a line if you zoom in. So the graph has to be a smooth line or a curve. It looks like a line when you zoom in. This is called local linearity. Oops. So it could be lots of curvy, but when you zoom in close enough to any point, it should look like a nice straight line. Not that that word matters that much. The derivative fails to exist, i.e. the function is not differentiable in 3 cases. And what I want you to think about is the first step is that the function has to be continuous. If the function's not continuous, it can't be differentiable. So here where we say it's going to be not differentiable if it's discontinuous. So if there is any kind of discontinuity, remember there are 3 kinds of discontinuity. Do you remember what they are? Infinite, removable, and jump. There are 3 kinds of discontinuity: infinite, removable, and jump. If any of those 3 kinds of discontinuity happen, your function cannot be differentiable. It has to be continuous to be differentiable. That's the first guarantee. The second thing, it has to be smooth. Okay, so it has to be smooth. So there can't be any sharp points, corners, or cusps. And the third thing is there can't be any vertical tangent lines. Kind of like in cube root of x. If you were thinking about the graph of cube root of x, it does this and it gets vertical kind of in the middle there, just for a second, but it does happen in the middle there, cube root of x does, okay? So a function is going to be not differentiable if it's not continuous, or if it has a corner or a cusp, or if it has a vertical tangent line. So I'm going to draw some graphs of these 3 things. Let me go back. I know I might have scrolled too fast. Vertical tangent lines. Yep, that says vertical tangent lines. So we don't want discontinuities. We don't want sharp points, and we don't want vertical tangent lines. If any of those 3 things happen, we say the function is not differentiable. So here's an example of each of those things. I mean, we know what examples of discontinuity look like. Here's one. So right here at this x value, it would be not differentiable. At all the other x values, you know, all the pieces and all the other points, it would still be differentiable. Okay, corners or cusps. They could look like this or like that. So right here at these sharp points, we would say it's not differentiable. And the last one is that vertical tangent, which I kind of drew for you up there. That's a terrible vertical tangent. Won't copy that one. Like that. So if you were to draw a tangent line right here, you would get a vertical line. And so that's bad, not differentiable. The best way to determine where a graph is differentiable and where it's not is to draw its picture. Yeah, so if you have an equation and you want to know where it's differentiable and where it's not, draw its picture. That's going to be your best method, okay? Okay, so here's two true or false questions. They're kind of the same question, just in a different order. My hint to you is that one of them is true and the other one is false. So don't say it yet. Let's just think for a second. The first one says differentiability implies continuity. So this says if a function is differentiable, then it's continuous. So if a function is differentiable, then it's continuous. If f is differentiable, then f is continuous. This one says the other direction. Continuity implies differentiability. If f is continuous, then f is differentiable. So what I want you to think about is which of these statements is true and which of these statements is false. Don't tell me yet though. Take like 30 seconds and make up your mind in your head. And tell me which of these statements do you think is true and which of these statements do you think is false?
Differentiability means the exact opposite of continuity?
No, differentiability means that none of these three things happen. These three things here. It means you can take the derivative. And if these three things happen, you can't take the derivative at those places. You can take the derivative other places, but not at those places. So if we talk more about this point right here, right? On this side, the derivative is what kind of number? A negative number, because that graph is going down, right? On this side, the derivative is what kind of number? Positive, because that graph is going up, right? So here the derivative is negative, here the derivative is positive. They're not going to meet, right? You have some negative numbers down here, like -1 is the slope down here. 1 is the slope up there. Those are not going to meet. So right at that sharp point right there, you're going to have a break in your derivative graph. So when we say differentiable, what we really mean is that the derivative graph is continuous. Right here at these points, the derivative graph is not going to be continuous. Right here at this point, the derivative graph is not going to be continuous because it's going to have like a vertical asymptote there. Okay, so when we talk about differentiable, what we're really saying is the derivative graph continuous? This one won't be because on this side, the slope is negative. On this side, the slope is positive. There'll be a jump discontinuity there. This one won't be because it's going to be a vertical asymptote right there. Same kind of thing. Okay, does everybody have their mind made up about these two statements? Which one you think is true and which one you think is false? Okay, if you think this is the true statement, raise your hand. Yeah, this is the true statement. So remember, true. This guy's true. This guy's false. Here are some examples, right? These three graphs right here are all continuous. Agree? These three pictures right here are all continuous, but they're not differentiable. So if you're continuous, you don't know anything. You could be differentiable, you could not be differentiable. But if you're differentiable, you have to be continuous. That's the first step. Okay, so here's another graph. And this says, where on this interval from -4 to 4 is the function differentiable? That's going to be lots of places, right? We might write that answer in interval notation. Where is it continuous but not differentiable? And where is it neither continuous nor differentiable? It might be easiest if we start from this last question and go back, right? So where on this graph is it neither continuous nor differentiable? So which points on this graph is it discontinuous and hence not differentiable? -2, there's a jump discontinuity there, yeah, and 2 has a what kind of discontinuity? A removable discontinuity. So this is not continuous or differentiable at x equals -2, jump, and x equals +2, removable. Is there any place on this graph where it's continuous but not differentiable? Yeah, at 0 there, that sharp point, that corner, that's I think that one's called a cusp, not a corner, but that point right there. Right there. X equals 0, it has a corner. or a cusp. So it's continuous there because I can draw that without lifting up my pencil, but it's not differentiable because of the tangent line. This would have a negative tangent line. This would have a positive tangent line. They wouldn't meet each other. So do you agree that everywhere else, this function is differentiable? All the points over here, this function is differentiable. All the points between here and here, this function is differentiable. All the points here, this function is differentiable. And all the points over there, this function is differentiable, yeah? So everywhere except, if I write it in words, I could say except -2, 0, and 2. If I'm going to put that in interval notation, I'm going to say from -4 to -2, from -2 to 0, and from 0 to 2. So I used this interval here, this interval here. Oops. Oh, and 2 to 4. I need one more interval. And 2 to 4. And that interval there. So I'm just leaving out those 3 bad points. I'm leaving out -2 because it wasn't continuous. I'm leaving out +2 because it wasn't continuous. I'm leaving out 0 because it wasn't differentiable. Everywhere else, see how it told me only to use -4 to 4? Everywhere else, differentiable. We use the square brackets if we want to include the point, but I don't want to include -2, 0, or 2, right? Because they were ones down there. Yeah, so I'm only using the parentheses because they started with parentheses. If they had looked at -4 and 4, then I would determine whether I want to use squares. I would say that 4 is probably a vertical tangent, so I would leave out 4, but because they left it out already, yeah. So square brackets if they started with square brackets, otherwise just use parentheses. Okay, let's do a little bit more interpreting. So this graph shows me the position of an object. Okay, this graph shows me the position of an object. The object is just moving on a straight line. Okay, it's just moving back and forth. That's all it's doing. Just moving on a straight line. Okay. What about this graph would tell me how fast the object is moving? The slope. The slope of this graph would tell me how fast the object is moving, right? The rate of change is the slope. So the slope is going to tell me how fast. Slope, which we call derivative, right? So S prime of t, yeah? So it's also going to tell me the direction that this object is moving, right? Like this object is traveling back and forth on a line. When is the object moving to the right and when is the object moving to the left? If the slope is a positive number, the object should be moving to the right, yeah? If the slope is a negative number, the object should be moving to the left. So this particle sort of starts here at 0. The particle starts right here at 0. He moves over here to what, like 2.25? To right there, yeah? That's this part of the graph. I'm not talking about how fast he's moving. I'm just talking about that part of the graph. Then he turns around and he comes back down to 2. So the particle turns around and he comes back down to 2. And then what does the particle do on this part right here, this flat part? Nothing. He just sits there for a long time, right? Like the particle like stopped and is eating some sort of bacteria or something, right? He just stopped and he's stuck there. Yeah. So he sits there for a really long time at that same point. And then when he gets here, he goes backwards still, right? To 1. So he goes back some more until 1. And then he turns around and like forgot something and goes back out until 2. So then he comes back this way until 2. So that's what the particle did, right? The particle started over here. It traveled this way kind of far, right? That was the farthest distance it traveled. Then it backed up. It was like, oh, I saw something fun back here. So it backed up. And then it sits there, that fun thing it saw, right? That's that yellow flat line where he's not moving. And then he's like, oh, let me go way back here and tell my friend or something, right? So he tells his friend, and then he's like, okay, now we're gonna go forward back to that fun yellow thing that we saw and hang out there some more. Yeah? So that's what that particle's doing. Okay? Everybody got it? This slope tells you how fast and in which direction. Because remember, velocity has two components to it. It has a number and it has a sign. Yeah, that's the difference between velocity and speed. Velocity has a number and a sign, positive or negative. Are you moving forward or are you moving backwards? And speed only has a number. Doesn't care whether you're going forwards or backwards. Okay, let's try to answer some questions now. Use this graph to determine the time intervals when the velocity is positive, negative, or zero. Make it a little bit smaller so I can see the picture and my words at the same time. Okay, where did we say the velocity of this dude is positive? When is this guy moving forward? In the green section, from 0 to like 1.5, right? From 0 to 1.5 in the green section here. Where else? 6 to 7, that light blue section at the end. So it's moving forward from 0 to 1.5 and from 6 to 7. So the green section and the light blue section. When the slopes are positive. Okay, so this section is when the slopes are positive. Okay, when is the velocity negative? Yeah, the pink section, 1.5 until 2. The pink section, 1.5 until 2, good. And that dark blue section from 5 to 6, when the slopes are negative. Okay, when's the velocity 0? The velocity is 0 when the dude's not moving, right? That flat line, that flat yellow line from 2 until 5. Bless you. That flat line from 2 until 5. Okay, now I want to talk about like how fast this dude's actually moving, right? So right at the beginning, this looks like he's moving kind of at a constant speed, right? Like he's just walking along at a constant speed. And then what happens? He slows down. Do you see right here when it starts to curve down, he's slowing down because he's like, oh, I gotta go back. I saw something cool, right? So he was over here, he's moving constantly at this speed. And then he's like, oh, wait, what was that? And he slows down. Yeah. And then what happens as he goes backwards? He speeds up until he gets there, right? And then he stops again. Yeah. So right here, he's speeding up until he gets there. Okay, then he stopped. And then what happens here? Yeah, he goes back kind of fast. And then he slows down again. Yeah. And then he kind of goes slower, getting faster, faster, faster until he's walking away. Yeah. Okay, so let's think about what this says. To determine when the acceleration, what's the acceleration? Yeah, the acceleration is the derivative of the derivative. Yeah, how fast the velocity is changing. I'm sorry? Yes. So this is velocity. Acceleration is going to be the second derivative, which we haven't talked a lot about, right? But we kind of got to think about it as when is this particle speeding up and when is this particle slowing down? But what I'm going to tell you is that there's an easier way to talk about the acceleration, okay? And it's the concavity of a graph. Does anyone know what concavity is? The shape, the bend of a graph. A graph that looks like this, kind of like a smiley face, is called concave up. And when a graph looks like this, the second derivative is positive. A graph that looks like this, kind of down like a frown, is concave down. And when it's concave down, the second derivative is negative. So when a graph is concave down, he's slowing down. When a graph is concave up, he's speeding up. And this is really hard to think about when you're going backwards. Yeah, but when we think about the slopes in terms of where they are in the number line, you remember last time when we did that number line and we had to think about like the really fast negatives were all the way over here and the kind of slow negatives were in the middle near zero. Remember that one from last time? That was hard. It's hard to order negative numbers, right? So small negative numbers are close to zero. Big negative numbers are far away from zero. When you're coming back towards zero, then you're speeding up, right? So you gotta think about it that way. So I'm going to color this graph again. New colors. And I'm going to say here, this graph is concave, whoops, down. Yeah, I'm going to say there, that graph is concave down. And then I'm going to say over here, this graph is concave up. And when we talked about this pink part of the graph, we said he starts off going kind of at the same speed and then he slows down. And then he gets fast in the negative direction, which means he's slowing down some more. He's accelerating in the negative direction. And then here, he's concave up, okay? So, because if you think about it right here, he's kind of going slowly and then he starts to walk faster, 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 faster. So he is slowing down in the pink section and speeding up in the yellow section. You got to think about those. You can't think about them in terms of an absolute value. You have to think about them on a number line. Yeah. This has like a slope of like positive 10. And then this one has a slope of positive 1. And then 0. And then negative 1 and then negative 5. You see how those numbers are moving to the right on the number line? This one has a slope of negative 10. And then negative 1. And then 0. And then 1. And then 5. And then 10. Those numbers are getting bigger on the number line. So he's speeding up because his numbers are getting bigger. He's slowing down because his numbers are getting smaller. It's hard to think about because you're like, but he's going faster here than he was there, right? But faster in the negative direction means he went farther to the right on the number line. Okay, so the acceleration is positive in that pink section up there, which was from 0 to 2. The acceleration is negative in that yellow section up there, which was from 5 to 7. And then it's 0 when he's just hanging out, right? 2 to 5. I guess that must be when he's flat right there hanging out. Oh, yeah, you're right. Strike that, reverse it. Reverse, reverse. Okay.
Curly brackets or square brackets?
Parentheses.
Okay.
Yeah. Yeah. So curly ones, is that what you call curly parentheses? In math, we have this thing, which is what we actually call curly. So yeah. If you've taken discrete, you've seen this, right? I don't know what to call them. Placeholders, holder inners. What do you want to call them? We can give them a new name.
Wait, I thought it was negative 0. That's 0.
Did I write the same thing again? Did I erase and write the same thing again? Negative, because it was concave down, and positive, because it was concave up. Yes, positive here. Think about the when he's going forward and the slopes are getting bigger. So when he's going forward and the slopes are getting bigger. Here, he's slowing down on this part right here. Slowing down right here. He's speeding up right there. Okay. I'm ready for Adfinity homework questions. This is a hard homework set, so I want to give you time in case you had questions. Adrian, go for it. 23, is that what you said? And 8, yeah. Let me pull 23. This is, oh wait, let me go to the, this one. Okay, 23 says the position in thousands of feet of a car driving along a straight road in time t in minutes is given by this function that's pictured below. Which graph, A through F, is the best representative of the derivative function? So what happens to this dude? He's going forward and then he, yeah, slows down and stops, right? So from here to here, from 2 to 3, what should his derivative be? 0, because he's stopped, right? Like that's when he's doing the fun thing, yeah? And then he goes which way? Back up again, right? And then from 5 to 7, he stops again, yeah? And then he speeds up, slows down. Do you see this? He's speeding up and then he slows down to stop. He speeds up and then he slows down to stop. He speeds up and then he slows down to stop. He speeds up and then he slows down to stop. So the slopes should go up and then back to 0. Be flat for a little bit. Up and then back to 0. Be flat for a little bit. Up and then back to 0. Yeah? He speeds up. He's going the fastest he can right here. He starts to slow down so that he can stop for that second. He speeds up. He's going the fastest he can right there at like 4. Starts to slow down so he can stop. He speeds up, starts to slow down. Okay, so let's look at these pictures. Oh, there's so many of them. It's not A because he never goes backwards, right? He's always moving away from home. So it's not A, it's not D, it's not E, and it's not F. So in mine, it's got to be B or C. What's the difference between B and C? Yeah. In C, he's not taking any breaks, right? He's just like going, he just like stops for a second and goes again. But in B, he's taking some breaks. Does he take breaks? Yeah, he takes breaks. Like for here, he breaks for a whole second. Like he's like, oh, I gotta catch my breath. And then here he breaks for like 2 seconds. So I'm gonna go with B for me. Let's see. Oh, there's more. Which of the following statements are true? Select all that apply. When S prime of t is positive, the car's position is decreasing. If the derivative is positive, what's happening? He's going up, right? He's increasing. Okay, so this one. The function S prime represents the acceleration. The function S prime represents the velocity. Which one? Velocity. Okay, good. If S prime of t is 0, then S must be 0. If the velocity is 0, then the position is 0. No, you remember when I was walking, right? Like I started here at 0 and I walked over here and I stopped. So my velocity was 0, but I was not at my house, right? I was like at the cool thing at the fair. Okay, so that one's false. When the car slows down, S prime of t is negative. No. When is S prime of t negative? When the car's going backwards. When the car goes backwards, S prime of t is negative. When the car slows down, S double prime of t, the acceleration is negative. Okay, so no. When S prime of t is 0, the car is stopped. When S prime of t is 0, the car is stopped. Yeah, okay, so mine were B, D, and G. I can hit submit. I don't know if I'll get it right though. I don't want to because I don't want to get it wrong. Yes, I agree. Okay, number 8. Let me get the snipper. You said 8, right, Shruti? Snip. 8. Let f of x be this function 2 plus 3 over x. Use the definition of the derivative to find f prime of x. Who remembers the definition of the derivative? Limit h approaches 0, good. F of x plus h minus f of x all over h. Okay, great. Let's try it. Limit as h goes to 0. F of x plus h is going to be 2 plus 3 over x plus h. Yeah, I just plug x plus h in there. So 2 plus 3 over x plus h minus f of x is just that function there. 2 plus 3 over x divided by h. I'm going to do a little bit of simplifying. What simplifying do you think I should do? Cancel those 2's. That's an excellent plan. Let's cancel those 2's. 3 over x plus h. Notice this minus sign goes with both terms. So put minus 3 over x there, all divided by h. Yeah, let's make a common denominator, right? Anytime you have 2 fractions, you should think combine the fractions together. So I'm going to make a common denominator. What's my common denominator going to be? X times x plus h, or x plus h times x. I'm going to multiply every term in my function, in my expression, by that thing, including the denominator. Okay, in this first term, the x plus h's cancel. In the second term, the x's cancel. So I'm left with limit as h goes to 0. In this one, I have 3x. In this one, I have minus 3 times x plus h divided by h times x plus h. Yeah, let's distribute the negative. That's a perfect plan. Limit as h goes to 0. 3x minus 3h over h times x plus h. Now, what do you want to do? Cancel those 3 x's. That's a good plan. Notice this is negative 3h, right? Be careful because that's what you're going to get wrong. Limit as h goes to 0, negative 3h over h times x plus h. Cancel the h's. Good idea. I like that plan. Limit as h goes to 0. I have negative 3 on the top, and I have x and x plus h on the bottom. Remember that I spent the time to write down that word limit every single time. How come? So I don't forget to do what? Plug in what? 0 for h. So I don't forget to plug in 0 for h. And because otherwise it's not mathematically correct. So I'm plugging 0 in here for h. When I plug 0 in here for h, I have x times x in the denominator, which is negative 3 over x squared. Okay? That's my derivative. So my derivative, f prime of x, is negative 3 over x squared. I'll give you a second to write so I can scroll up and see what the other question asked for. I can't remember if it's on there or not. I mean, you do it at home, so you could look it up, right? You mean like the midterm? Like the quiz on Monday? I think it's on the top of the quiz, but you could look it up in your notebook. Yes, sir. Right here. I don't cancel it. I put 0 in for h, and then x plus 0 makes x. X times x makes x squared. Yeah. No. I'm trying to think of what formula sheet you might need. No, I'm going to say no. I might change my mind later, but I'm going to say no right now. Can't think of any formulas. I mean, this is really the only formula that we've done, right? We haven't done any other formulas, have we? And Oftentimes, if I ask you to use this definition, then I put it in the question. I can't remember. I don't have like the quiz. It's on my other computer. So I can't look and tell you whether it's there or not. I just can't remember. Okay, part B says use the derivative to find the slope of the tangent line at x equals 2. Plug in 2 to that derivative. F prime of 2 is negative 3 over 2 squared. Negative 3/4. What that means is if I graph that function, 2 plus 3 over x, if I graph this function and I go to x equals 2, it should be going down with a slope of negative 3/4. More homework questions. Three. Three. Let f of x equal 4x squared minus 4x plus 11. Use this definition, this is that other definition of the derivative, to find the slope of the tangent line to the graph at the point a equals 1. Okay, so if I'm going to use this definition at the point a equals 1, then I'm going to do limit as x approaches 1, that's my a value, f of x minus f of 1 over x minus 1. I feel like I did this one on Wednesday. Did I? I think so. Okay, so I need f of 1 right here. So to find f of 1, I plug it into this equation. 4 times 1 squared minus 4 times 1 plus 11. Oh, no, I know what happens. I think this is the one you asked me after class, right, Adrian? Okay, so 4 minus 4 plus 11 is 11. So this is going to go right here. Limit as x approaches 1. F of x, that's this guy. 4x squared minus 4x plus 11 minus f of 1, that's that thing I just computed, 11 over x minus 1. All right, what do you want to do? Factor. I'm not going to factor yet, though. I'm going to combine like terms first. And when I do that, I get 11 minus 11 and they cancel. So I have 4x squared minus 4x over x minus 1. And now I'm going to factor. That was a good plan. How should I factor this guy? Take out the greatest common factor. What's the greatest common factor here? 4x. So I'm going to take out a 4x. When I take 4x out of this one, 4x squared divided by 4x leaves me with x. 4x divided by 4x leaves me with minus 1 over x minus 1. Luckily, they can cancel, right? Remember, my goal was to get rid of that x minus 1 because I didn't want 0 in the denominator. Now that he's gone, I've got one more step. It's the whole reason that I wrote limit every single time. Plug in 1 for x. Okay, so the slope is 4. Now I need to find the equation. I know that the slope is 4, and I know the point. Remember, the x value was 1, and the y value was this yellow thing that I computed, was 11. So you can use point slope form. You can use y equals mx plus b form and solve for b, whatever your favorite method is. Mine's point slope, but I don't care what yours is. I'm flexible. Y minus 11 is m 4 times x minus 1. Distribute. Add 11 to both sides. So m is 4 and b is 7. Other questions from the homework? 22. You were gonna say the same one? No, wait. Christian, go ahead, tell me.
Yeah, number 6.
6 and 22. Oh, 6 is a good one. Not that 22 is not, I just didn't look at it yet. Okay, 6. If f of x is square root 4 plus 5x, find f prime of 2 using this definition. This is that other definition again, right? F of 2 is the limit as x approaches. What's my a value in this one? 2, because 2 is what's inside that function. Limit as x approaches 2 of the expression. So limit as x approaches 2, f of x minus f of 2 over x minus 2. So I need to find f of 2. I'm going to use f of 2 in this equation. 4 plus 5 times 2, square root 14. So f of 2 is this thing. So I have limit as x approaches to f of x, which is my function, square root 4 plus 5x, minus f of 2, which is square root 14, over x minus 2. That's what goes in that box. So this thing right here goes in that box without the limit in the front, just the stuff in the inside, okay? And then to get the last one, I have to find this limit. How do I find this limit? There are 3 ways to find a limit when you have 0 in the denominator. They are rationalize, factor, combine fractions, right? This one has square roots, so I'm going to rationalize. To rationalize, it means multiply by the conjugate. The conjugate is this same expression with the opposite sign here. So instead of doing subtract here, I'm going to do add. So same expression with the opposite sign. Okay. Limit as x approaches 2. I'm not going to change the denominator because my goal is that that x plus x minus 2 is just going to cancel out, I hope. And in the numerator, I'm going to do first these two. Square root 4 plus 5x times square root 4 plus 5x makes 4 plus 5x. Okay, outside. So I'm going to do this one times this one, which is plus square root 4 plus 5x times square root 14. Inside, which is this one times this one. So minus square root 4 plus 5x times square root 14. And then last, which is, I don't know what color to use, this one times this one. So negative square root 14 times square root 14 makes 14. Okay, I noticed that this guy and this guy are exactly the same, but with opposite signs. So I can cancel out those inside terms. That's the goal of rationalizing, right? To cancel out those middle terms. And now I don't have any more square roots in the top. Oops. Limit as x approaches 2. In the top, I have 4 plus 5x minus 14. So that's 5x minus 10, because 4 minus 14 makes negative 10. X minus 2, and then this whole big thing here. So remember, I was trying to get rid of this x minus 2, yeah? It still didn't go away. What should I try next? Factor. Let's factor the numerator. And I'm going to factor the numerator. I'm just going to do it over here on the side. I'm not going to write it all again. Mostly because I'm lazy and it's Friday. Okay, that numerator looks like 5 times x minus 2. Now those x minus 2's cancel. So I have limit as x approaches 2. 5 is left in the numerator. And square root 4 plus 5x plus square root 14. What's left? Plug in 2 for x. Plug in 2 for x. So it's 5 over, this is square root 14. Square root 14 plus square root 14 is 2 square roots of 14. I don't know if it needs like a nice number like that, or if you can put that in your calculator and get that decimal. I don't know what decimal is going to take. Infinity is going to take. Guess and check, I guess. sideways. Of course it is. One more.
Mine is actually 24.
Oh, yours was 24, not 22. Okay. Did someone else say 22? Yes. Okay. This is 22, and then I'm going to go to Matthew's, which was 24, not 22. Okay, this one's hard to see because it's tiny. Let's see if I can make it bigger. It's going to fall off the screen if I try to make it bigger. There's the graph. A child fills a pail by using a water hose. After finishing, the child plays in a sandbox for a while before tipping the pail over to empty it. If V of t gives the volume of water in the pail at time t, then the figure below shows V prime of t. This figure shows the derivative. This figure doesn't show the volume, right? This figure shows the derivative. The derivative tells you how fast the volume is changing. Okay, so that's a really tricky part. This figure is showing you the derivative. At what time does the child begin to fill the pail? He begins to fill the pail when the volume, when the derivative is a positive number. Here, the derivative is 0, right? Here, the derivative is 0, nothing's happening. He's not putting any water in the pail. Here, the derivative is 0. That's when he must be like playing in the sandbox, right? Between these 2 points, 3 and whatever that is, 4, 5, 6, 7, 8, 9. Between 3 and 9, he's filling the pail with water. Well, no, here he's not. He pours some water in, he lets it sit, he pours some more water in. Yeah, even though it's going down, he's still pouring more water in because the derivative, the rate of change is positive. Then he's playing in the sandbox. He dumps the water out, and then he dumps more water out. Okay, so he dumps a little bit of water out, stops, dumps some more water out. Okay, so when does he begin to fill the pail? Right there at t equals 3. When does he finish filling the pail? Yeah, when it stops being positive, right here at 9. And when does he tip the pail over? When the volume starts to come out, right? When the rate of change is negative, he's pouring water out of the pail. So all of these places below the x-axis, when he's pouring water out of the pail, and he starts right here at 10, 11, 12, 13, 14, it looks like. Okay. I gotta find a blank page. I gotta make one. I don't have it. Right here and see how it goes. Uh, 24. Apparently we're going with green now. An object moves along the y-axis marked in feet so that its position at time t x in seconds is given at time x in seconds is given by the function f of x equals 208x minus 16x squared. Find each of the following. The instantaneous velocity v equals f prime of x. How do you find the derivative? The limit as h approaches 0 of f of x plus h minus f of x all over h. Limit as h approaches 0, f of x plus h minus f of x all over h. On Monday, we'll get to learn some shortcuts. For your quiz Monday, you still have to do the rules. You still have to use the definition. If you do not use the definition on your quiz on Monday, you will fail. Take it as your drop if you want to, but that's what I'm telling you now. Got to use the definition on your quiz on Monday. Okay, I got to find f of x plus h. So that's 208 times x plus h minus 16 times x plus h squared. So 208x plus 208h minus 16 times. When I do x plus h squared, I'm going to do x plus h times x plus h, which gives me x squared plus 2xh plus h squared. If you did your homework already, then you know that you use this like 100 times. Okay, keep simplifying. 208x, 208h. I'm going to distribute this 16 to all three of those pieces. 16x squared, 32xh minus 16h squared. That's f of x plus h. That's what goes in right here. Equals limit as h goes to 0. 208x plus 208h, 16x squared, 32xh, 16h squared, minus f of x, darn, 208x minus 16x squared. I just squeezed that in there. I apologize. Okay, all divided by h. Remember we said at this point, everybody without an h should cancel. I have 208x's here minus 208x's there. I have negative 16x squareds here minus negative 16x squareds there. So when I cancel them, I get limit as h goes to 0, 208h minus 32xh minus 16h squared divided by h. Yeah, everybody has to have an h. If everybody doesn't have an h, you've made an error. Everybody has to have an h. You're going to cancel one h from each term. So cancel one h from each term. H here, one of these, and h there. Limit as h goes to 0 of 208 minus 32x minus 16h. What's the last step? Plug in the 0 for h. So 16 times 0, that guy's not going to count anymore. 208 minus 32x. So my f prime of x, or my velocity, is 208 minus 32x. Part B says find the velocity when x equals 1 and when x equals 7. What are you going to do to find the velocity when x equals 1 and when x equals 7? Plug in 1, 7 into this formula, right? Luckily, we found this formula, or we'd have to do that limit thing over and over again. That would be really, really crappy, right? It was already crappy enough. Now we'd have to do that limit thing again. I'm going to plug 1 into this velocity equation. I'm going to plug 7 into that velocity equation. F prime of 1, 208 times 32, minus 32 times 1. Oh, that's hard. 176. Feet per second. I think it's in feet per second. Yeah. Okay, F prime of 7. 208 minus 32 times 7. Oh, that's even harder. 214, 224, negative 16. Someone should put that in their calculator. 210 plus 14 is 224. Oh, I'm more confident. Negative 16. Okay, part C says, when is the velocity 0? When is the velocity 0? How are you going to determine when the velocity is 0? Yeah, take this velocity equation right here and set it equal to 0. We know it happens somewhere between 1 and 7, because at 1, the velocity is a big positive number. At 7, the velocity is a negative number. To get there, it has to go through 0. So we know it's going to happen somewhere between 1 and 7. So I'm going to take that velocity function, 208 minus 32x. I'm going to set it equal to 0. I'm going to solve for x. So add 32x, divide by 32, x equals 6, 180, 192, 7. 7 was too big. Somewhere between 6 and 7. What number do you get here? How many? Exactly? No? Is it wrong? 6.5 seconds. So after 6.5 seconds, the velocity is 0. This dude's not moving anymore. If I had graphed this function that I started with, 208x minus 16x squared, that maximum would be at 6.5 seconds. He goes up, 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 his velocity is positive. He stops at the top, he starts to fall down, okay? All right. Oh, the second, I put it in the announcements, but the second learning thing, the math learning project, mindset learning project is due Wednesday, okay? And then we have a break because it's Labor Day. But the second one is due Wednesday night. This one will take a little bit longer because you gotta watch some sort of video before you do your quiz. So, all right, have a great weekend, guys.